Graphs are everywhere, and Fetch is no exception. In the AI domain at Fetch, we are using graph neural nets to build graph representations of receipts and learn how different pieces of text connect to form meaningful receipt items. Globally, we can represent the entire structure of Fetch data as one big graph where users are connected to each other through referrals, scans are connected to users, and so on. Graph neural nets can learn a ton of valuable things about user behavior, value of offers, fraud, etc. Visualization is a big part of machine learning development process. Visualizing the data that goes into the neural net helps us ascertain that we are indeed feeding the training AI the correct information. While it is simple enough to visualize regular AI training data, such as text or images, visualizing graphs requires some work. On the other hand, graphs carry a lot more information about the data. They carry structure, so examining those structures for bugs and developing a feel for the data is more interesting than in the case of a regular AI. I set out to build a tool to visualize graphs in all their richness and give the user an ability to interact with them. To capture this interactive gaming aspect of the tool, I am using the Unity game engine to develop it. If we create a graph at random, it's going to be pretty bad. Edges are crossing over, and even though we are in 3D, there is a huge amount of entanglement that prevents us from seeing things clearly. We start by enabling a few layout algorithms. Our goal is to disentangle the edges to make the graph aesthetically more pleasing if possible. Force layout algorithms are based on the idea that graph nodes exercise repulsing forces on each other, while all connected nodes also attract. Eads algorithm is a classic example of this. The nodes are connected by springs that exert repulsion and attraction forces. This can be tuned with a couple of constants. Forsterman-Reingold algorithm introduces the notion of temperature, can't run too far away when it's cold, and is conscious about screen dimensions. Kamada-Kawai is an optimization-based algorithm trying to find the position of each vertex by iteratively minimizing an energy function. Which one is your favorite? Large graphs require combinations of these algorithms to produce meaningful layouts, so the work is just beginning. Moving to the GPU and enabling huge graph layouts are the big steps for the project code named Unigraph. It's been a lot of fun getting thus far, and I look forward to continuing the journey.